Hello students, in the previous class we have gone through the barometers, manometers, and also we have started the fluid dynamics, that is streamline flow, continuity equation. We have also seen the definitions of laminar flow and the turbulent flow. So moving forward with the fluid dynamics, that is in the today's class we are studying the energy possessed by a liquid in motion. Which type of the energy a liquid possesses when it starts to move. See, a liquid in a motion will have a three types of energies, that are the potential energy, kinetic energy, and the pressure energy. The kinetic energy means it is a energy which is possessed by a liquid by the virtue of its motion. As we know that the kinetic energy means it is an energy possessed by a liquid by its motion. So consider a liquid having a mass of m and the velocity v with which it is moving. So the kinetic energy of a liquid, we are going to write it as a half mv square. So it is the kinetic energy of a liquid. If we want to calculate this kinetic energy of a liquid per unit volume, if you want it for a per unit volume, then we will have 1 by 2 mv square whole divided by the volume v. That will be given as, we know that mass divided by volume will give the density. So 1 by 2 mv square by volume v will be given as half rho v square, which is the kinetic energy per unit volume of a liquid. And next, it is having the potential energy. The potential energy means this is the energy possessed by a liquid by virtue of its position. So we know the potential energy definition, and this equation is the potential energy will be equal to the mgh, where m is the mass of the liquid, g is the acceleration due to gravity, and h is the height of the liquid from a reference line. So the potential energy of a liquid is given by mgh, and the potential energy per unit volume will be given as mgh divided by v. Here also we are having m divided by v, which gives the density of the liquid. So we will have potential energy per unit volume of the liquid as rho gh, where rho is the density of the liquid, g is the acceleration due to gravity, and h is the height of the liquid from a reference line. Next we are having the pressure energy. Pressure energy means the energy possessed by a liquid by virtue of its pressure. That is known as a pressure energy. When we apply certain pressure on a liquid, then using that pressure, what is the energy it possesses due to that pressure whatever we have applied, that is known as a pressure energy. To know about this pressure energy, we will consider a cylindrical tank. See, consider this cylindrical tank which is filled with a fluid which is having the density as rho. We are having a cylindrical tank, this one, and in which a liquid is filled which is having the density as rho. So, and this cylindrical tank is having a side tube. See, this is a narrow side tube which is having the area of cross section as A. The area of cross section of that side tube is A, and it is also having a movable piston. See this one. This is a movable piston. When this piston is moved inside, if we apply certain pressure for that piston, then this piston moves inside this tank, means it is the earlier position of that piston, and this is the later position of that piston. So when we apply certain force on that piston, it moves with the distance x. This is the x is the distance covered by the piston when we apply certain force on that piston from outward to inward motion. So this piston is moved from this place to this place, crossing a distance of x. So the force on a piston will be, we know that we have applied a p amount of force. We know that we have applied a p amount of pressure on that piston. So what is the force applied on that piston will be p into a, because we know the equation of pressure, that is pressure is equal to force divided by area. So we know the pressure and we know the area of cross section. We are going to find out the force on that piston. So force F is equal to P into A, that is P is the pressure and A is the area of cross section of this side tube. So we have the distance which is covered by this piston, and we know the force acting on that piston. So we can easily find out the work done of that piston. So that will be work done is equal to, we have work done is equal to force into displacement. So we know the force, that is P into A, and we know the displacement, that is x. So work done is equal to PAX. Name it as a equation number A. So next, the mass of the liquid move into the tank. We have applied certain pressure on that piston. So whatever the liquid which was there earlier in this position, that has moved inside the tank. So what is the mass of that liquid which has moved inside the tank? That will be m is equal to rho AX, because we know the density of the liquid. The density of the liquid we are knowing, and we know the volume, that is C by this equation. Density is equal to m divided by v, that is mass divided by volume. We are going to find out the mass value. Then mass will be equal to density into volume. We know the density of the liquid, that is rho, and we know the volume of the liquid, that is, because by this equation volume will be equal to area of cross section into the length or the distance. So V will be equal to area into the distance. So area we are knowing that is A, and L means the distance which is covered, that is x. So the mass of the liquid which has moved inside the tank, that will be m is equal to rho AX. So by this equation B, what will be the value of A into x? That will be AX is equal to m divided by rho. So substitute this value of B into equation A. So we will get the work done equal to Pm divided by rho. So this is the pressure energy, or this work done is stored as the pressure energy, and this is known as a pressure energy of that liquid. And we can modify this equation also. See, we know that density is equal to m divided by v, that is mass divided by volume. So we will have the volume equal to mass divided by density. Here we are having m divided by rho, that will be replaced as the volume. So work done will be equal to P into V, where P is equal to pressure and V is the volume of the liquid. So this is the work done of that liquid, or the the pressure energy of the liquid. So work done per unit volume will be equal to, that is, PV divided by V will be equal to P. This is the work done per unit volume of the liquid. This is about the energy possessed by the liquid in its motion, that is kinetic energy, potential energy and the pressure energy. We are going to use these terms in the next concepts. The next concept is the Bernoulli's principle. The Bernoulli's principle states that for a streamlined flow of an incompressible non-viscous fluid, the sum of the potential energy, kinetic energy and pressure energy per unit volume remains constant. This is the statement of Bernoulli's principle. See what it says. For a streamlined flow, we know the streamlined flow. In the last class we have studied this one. Streamlined flow means it is a steady flow of that liquid. In this we are having the incompressible and non-viscous fluid. We know the incompressible. Incompressible mean what? On applying a external pressure on any liquid or a fluid, if the volume of that fluid remains as it is, then that type of fluid we are going to call it as a incompressible fluid. So this is about incompressible. And we have the non-viscous fluid. Non-viscous means what? As we know that when the fluid is moving, it has the several layers of the fluids. If these layers, we know these layers are moving with the different velocities, but if they are not interacting with each other, or if there is no any force of friction between any two layers of that fluid, then that type of fluid is known as non-viscous fluid. Non-viscous fluid means it is a fluid in which the layers of the fluids are not having any force of friction. Then that type of fluid is known as non-viscous fluid. And if a fluid is incompressible and also non-viscous, then that type of fluid is known as a ideal fluid. So in Bernoulli's principle we are having, if an ideal fluid is moving with a streamlined flow, if an ideal fluid is having a streamlined flow, then the sum of its potential energy, kinetic energy and the pressure energy per unit volume remains constant at any point of that flow. This is about the statement of Bernoulli's principle. We can also write it as the pressure energy plus kinetic energy plus potential energy is equal to constant. In the previous part we have studied about the pressure energy, that is per unit volume they have said here. So the pressure energy per unit volume we have as a P. So pressure energy as P plus kinetic energy. In this kinetic energy we are having the kinetic energy per unit volume as half rho V square. So plus half rho V square plus potential energy per unit volume as rho GH. So plus rho GH. These all are equal to constant in case of a ideal fluid having a streamlined flow. So this is about the statement of the Bernoulli's principle. Let us say about the proof of this Bernoulli's principle. See, consider a pipe. Consider this pipe which is having a varying in a area of cross section. As you can see, the area at this point is larger than this point. So consider a ideal fluid. Ideal fluid means a fluid which is incompressible and also non-viscous. That type of fluid is flowing in the having a streamlined flow in case of in the this pipe. So as this pipe is having a variation in the area of cross section, at this point, at the point A, the area of cross section of that pipe is larger than the area of cross section at point B. Let us take P1 VA1 H1 V1 and the P2 A2 H2 V2 as, see, P1 is the pressure, A1 is the area of cross section, and H1 is the height of the pipe, and V1 is the velocity of the fluid at the point A. At point A, whatever the fluid is flowing, which is having a pressure P1, area of cross section as A1, and height, see, from the reference line. Here we are taking the reference line as a earth surface. From the earth surface, the end A is having the height of H1 and A1 as the area of cross section and V1 as the velocity of the fluid and small a1 as the area of cross section and P1 as the pressure at the point A. So similarly at point B, P2 is the pressure of the fluid, A2 is the area of cross section at the point B, and H2 is the height of the end B, and V2 is the velocity of the fluid at the point B. So next, this is about the setup. Next, see the force acting on A due to the pressure P1. At the end A, we are applying the pressure P1, so that what is the force acting on this point A? That will be equal to P1 into A1. We know that pressure is equal to force divided by area. Pressure is equal to force divided by area. So force is equal to pressure into area, and at the end A we are having the area of cross section as E1. So force is equal to pressure into area, that is P1 into A1. This is at the end A. Next, the distance travelled by the fluid in time t. Let us take a small element A dash. Distance travelled by the fluid in time t is given by how much distance thus the fluid has covered in a time t. We are going to measure and we are going to see, we have taken that it has covered the area A to A dash. Suppose, so the distance will be V1 into t, because velocity is equal to distance divided by time, and here we are finding the distance. So that distance is equal to velocity into time. So we know the velocity of the fluid and we know the time. So velocity into time gives us the distance covered by the fluid. So that will be V1 into t. And by these two equations we got to know about the force acting on a end A and the distance travelled by the fluid at the end A. So the work done on the fluid will be given as force into distance. So we know the force, that is P1 A1, and we know the distance V1 T. So the work done at the point A is W1 is equal to P1 A1 V1 T. And similarly at the point B also we are calculating the force and distance. So the work done on the fluid at point B is equal to W2 is equal to P2 A2 V2 into T. See, as the fluid has moved here from A to A dash and here from B to B dash. Take this only area. See this A to A dash. Consider, we know the area, that is A, and we know the distance it has covered, that is V into C. So we can write this A into V into T as the volume, that is the volume of this cylinder. So A into V into T is equal to the volume. Substituting this for both equations W1 and W2, we will get as W1 is equal to P1 into this A1 V1 T is changed as a volume V1 due to this equation. So this W2 will be P2 V2 because P2 is as it is, and in A2 V2 T, from this equation it has changed to the volume V2. So we know that volume as equal to the mass divided by density by this relation. So the W1 can be written as P1 m divided by rho, and W2 can be written as P2 m divided by rho. This W1 is the work done on the fluid at the point A, and W2 is the work done on the fluid at the point B. So the net work done on the fluid by the pressure energy will be W is equal to W1 minus W2. This W is equal to W1 minus W2 gives us the net work done on the fluid by pressure energy. So that will be equal to, by using these two equations, we will get the W equation as W is equal to P1 m divided by rho minus P2 m divided by rho. Name it as a equation 1. Next, whatever the work done we have got, that is by applying a certain pressure at this end and at the pressure at this end. So when we apply certain pressure at this end A, that pressure we are applying, that is the work done by pressure on a fluid on applying at point A, that will be giving rise to the increase in the kinetic energy and the potential energy, because at initially when it was at A point, the kinetic energy was 0. So when we apply certain pressure at the end A to this fluid, then the fluid starts to move. So as the fluid is moving through this tube, it's gaining the kinetic energy. So on applying the pressure energy at the point A, the kinetic energy goes on increasing from A to B point. So like that only the potential energy. Initially the potential energy was at having the, that is, this will be having the mgh1. Consider at a point A, the potential energy was, it was having certain potential energy because it was at a rest position, so it will have certain potential energy. But we know that the potential energy is depending on the mass, gravity and the height, because potential energy will be equal to the, by this equation only, the potential energy is equal to the mgh value. Here we are having the mass of the fluid as a constant, and g, the acceleration due to gravity will be constant. Here it depends on only the value of height, and in this setup we have set it as the h1. A point A was at the height of h1 and the point B was at the height of h2, where h2 is greater than the h1. So the potential energy, whatever it was there at point A, that is also goes on increasing when the fluid goes from A to B, because the height is varying here. So in generally we are saying that this work done, whatever the pressure energy we have applied on the fluid, that increases the kinetic energy and the potential energy of the fluid when it flows from the A to B. So we will have the increase in kinetic energy of the fluid, as the kinetic energy goes on increasing from A to B. So to get how much value it has increased, we have to subtract the kinetic energy whatever it has at the point B minus kinetic energy at the point A. So the increase in kinetic energy of the fluid will be equal to kinetic energy at point B minus kinetic energy at point A. And we know that kinetic energy at point B will be 1 by 2 mv2 square, because at the point B the velocity of the fluid is v2. So 1 by 2 mv2 square minus kinetic energy at point A will be 1 by 2 mv1 square. This is the increase in kinetic energy of the fluid. Take it as a equation number 2. Next we have the increase in potential energy of the fluid. That will be also same as this equation, that is the potential energy at B minus potential energy at point A, because the potential energy is also increasing, so it will be maximum at the point B and minimum at the point A. So maximum value minus minimum value will give us the how much value it has increased. So the potential energy at point B will be mgh2 minus mgh1. This is the increase in potential energy of the fluid. Take it as a equation number 3. So by taking the according to the conservation of energy, we know that conservation of energy, that is the total energy of the system is always constant. So the work done on the fluid is equal to the change in the energy of the fluid. We can say like this, that is how much work done or the pressure energy we had given, that will be equal to the change in the energy of the fluid. So that is, we can write it as the work done by pressure energy is equal to the total increase in energy, and the total increase in energy is due to the both kinetic energy and the potential energy. So substituting by using equation 1, 2, 3, we will write it as the work done by pressure energy will be this W value, that is P1m divided by rho minus P2m divided by rho, that is equal to the total increasing energy will be the sum of both kinetic energy and potential energy. So mgh2 minus mgh1, this is the potential energy plus kinetic energy, that will be 1 by 2 mv2 square minus 1 by 2 mv1 square. Rearrange these two terms, that is take the one terms at a one side, that is the subscript 1, this P1m divided by rho plus mgh1 we are sending this minus mgh1 to the left hand side, so that will become plus mgh1. Next plus this minus 1 by 2 mv1 square, we are sending it to the left side, so that will become plus half mv1 square. Then that will be equal to the, we are sending this minus p2m divided by rho to the RHS, so that will be plus p2m divided by rho plus mgh2 plus half mv2 square. We have separated the first and second points, that is the terms with corresponding to the end A is equal to the terms corresponding to the point B. See, these P1 m divided by rho plus mgh1 plus divided by 1 divided by 2 mv1 square, that is equal to P2 m divided by rho plus mgh2 plus half mv2 square. This LHS is with respect to end A and this RHS is equal to the end B. So divide this above equation by rho by m. On the both sides we will get as P1 plus rho gh1 plus 1 by 2 rho v1 square, that is equal to P2 plus rho gh2 plus 1 by 2 rho v2 square. This LHS is due to the point A and RHS is due to the point B. So in generally this point A is equal to the corresponding points of B. So in generally we can write it as P plus rho gh plus half rho v square is equal to constant. And this equation 4 is known as a Bernoulli's equation. And see, which is we have derived, that is equal to the statement, that is P plus half rho v square plus rho gh is equal to constant, and this equation is also same. So we have derived the Bernoulli's principle, and this Bernoulli's principle is holds good only for the non-viscous fluid, because as we have used the energy conservation principle in this here. So as energy conservation has used, so what it says, there is no any energy is lost due to the friction, but when the fluids flows there will be the loss of the energy due to the internal layers friction. So as different layers of the fluids are moving with the different velocities, so there is a friction between those layers of that fluid, so which is leads to the energy loss. So that's why we have considered here the whatever the liquid will be or a fluid will be, that must be non-viscous to get a undiminished energy. That's why we have considered here the non-viscous fluids, and this Bernoulli's principle holds good only for the non-viscous fluids, and also it is only applicable for the incompressible fluids, and also it is applicable only for the steady flow or a streamlined flow fluids. Because if we consider a turbulent flow or a non-steady flow, then there's velocity and the pressure are continuously changing. So that's why in Bernoulli's principle it is not applicable. That's why this Bernoulli's principle is not applied for the turbulent flow or a non-steady flow. And when the fluid is at rest. In this equation 4 only, if the fluid is at rest, then that time the velocity v will be equal to 0. Then the equation of Bernoulli's equation will be equal to P1 plus rho g H1 is equal to P2 plus rho g H2, because of the velocity is equal to 0, the kinetic energy term will be vanished. So whatever the terms will be, that because of the pressure energy and the potential energy. So P1 plus rho g H1 is equal to P2 plus rho g H2. That will be equal to, we can write it as P1 minus P2 is equal to rho g H2 minus H1. And this is about the Bernoulli's principle.